is enough?
No.
So, can you hear me? Huh? You got the right one? Let me try. Is it fine now? Yeah, okay, I have to get away from this one.
It's the one. You hear me? Yeah, I can hear you, but can you just tap?
What do you mean tap?
Well, just
Yeah.
See if the microphone.
See if it's the microphone of your computer. Tap on the microphone.
Yeah, where is that now?
I think it's near your phone.
No, but I can just take a step away from here, and if you can still hear me, can you hear me fine? Okay, then it shouldn't be that one there.
Can you put it a bit away from your mouth? Yeah. So, what I do?
You fine now?
It's saturated, so can you put the volume a bit down?
Yeah, let me try then. You better now?
Yeah, it's good.
Okay, awesome.
Wait 1 minute.
You're in charge. So this is supposed to be 45 minutes.
Yes, 45. You take 5 minutes. People may ask questions during the talk. Sometimes it goes a bit beyond. Okay. We start. Good morning, everyone. It's a pleasure to introduce today's speaker, Alexandra Barreira. So Alexandra is PhD at the University of Durham in the UK under the supervision of Baiju. At the time, he was working on modified gravity and test modified gravity in cosmology. And now he did a postdoc at the Max Planck Institute for Astrophysics, and now he's an Origin Fellow at the University of Munich. And he did a lot of great contribution on understanding the connection between the visible matter in the universe and the invisible matter in the universe, the dark sector, and what we call galaxy bias. So today we will talk about this and why it is important to understand galaxy bias to extract information about fundamental physics in cosmology. Staging your side.
All right, thanks a lot for the introduction. Before I start, thanks for having me. Thanks for the invitation. I really enjoy knowing how you do things around here. You invite the speaker, you stuff them with raclette and cheese, and then you force them to give a talk. the next day. So that's really nice. So thanks a lot for that. And special thanks to you, Francesca and Andre, who's not here. You were very kind and helpful in organizing this visit. Yeah, and I don't know also you do things around here, but I welcome questions throughout. So feel free to interrupt me at any time. Okay, so this is the title of my talk, as Francesca said, Connecting the Visible to the Dark Universe, but more specifically, this is going to be about something called galaxy bias and its impact in our ability to extract cosmological parameters from data. Okay, so this is going to be a large-scale structure talk. Here's a one-slide introduction to it. So this is how we think the large-scale structure looks like. This is realistic in that it comes from a realistic n-body simulation of structure affirmation. Let me play the movie again. So the density field starts off, as we all know, close to homogeneous. There are tiny density fluctuations, which we believe were generated by quantum fluctuations during inflation. And then, as you just saw, primarily through gravitational instability, these fluctuations grow. And at the end of the day, we have this thing that looks like a complicated web. Some people refer to this as the cosmic web. And then you can identify these filaments that shape these emptier regions that we call voids, and along the filaments and where they intersect, we encounter gravitationally bound objects that we call dark matter halos. Okay, so our life in large-scale structure is basically to extract cosmological information out of this complicated field, and this is, of course, very challenging for several reasons. First of all, you cannot tell by eye, but this is a very highly nonlinear field. So the density contrast here ranges from order unity and negative inside the voids, and can go all the way to order positive and sometimes 1,000, very deep inside dark matter halos. So this means correlation theory only takes you so far. Like very often, you have to rely on simulations like this one to make predictions. And on top of that, you can now tell by eye that this is a very non-Gaussian field, and this means simple statistics like the power spectrum do not capture all of the statistical information of this field, because that's only true. The power spectrum is only a complete representation of the information content of a field. If that field is Gaussian, this one is clearly not. But yes, but if our life wasn't hard enough by the fact that this field is nonlinear and non-Gaussian, our life is made even harder by the fact that, as Francesca alluded in the introduction, we don't even get to see it, right? And this is, now I'm just flipping between the same region in the simulation. This is a simulation known as called Illustrious TNG. It's a very famous hydrodynamical simulation of galaxy formation. And what I'm doing here is just flipping between showing the whole mass and just the mass that ended up in stars, which is what we would be observing. And I really like to flip a few times between this to really help appreciate how much of this information, how much of this rich structure goes away when we restrict ourselves to just the visible component. Of course, this has to do with the fact that most of the mass in the universe is in the form of dark matter. There's a reason why dark matter is called dark. We don't get to see it. And so we have this additional challenge of having to extract information on cosmology, but we only have access to 15% of this field in mass, which is what's in the form of stars and gas inside galaxies and galaxy clusters. Okay, so let me flash a few more of these pictures. So here again, the large-scale structure on the left and the stars on the right. Stars are not the only way we have to probe the universe. Another famous example of another tracer is the case of the diffuse gas that's in the form of neutral hydrogen, which emits 21 centimeter photons. And a point I want to make here is that if I zoom on the left, if I zoom on a dark matter halo, on the right, we encounter a large concentration in stars, but we do not find any H1. So there is gas here still, of course, but it's just not in neutral form. So the only point that I want to make here is that depending on how we choose to observe the universe, we're going to probe the underlying large-scale structure, not only in quantitative, but also in qualitative different ways. Here's, let me show a few more of these examples. So here's the location of galaxies that in this model are not forming stars at any significant rate, so quenched galaxies. We can compare that with their star-forming counterparts. Again, you can see some similarities, but some differences. All galaxies with a stellar mass larger than 10 to the 9 solar masses, 10 to the 10 and 10 to the 11. And this already tells us a few things about biasing, which is that as I restrict myself to more massive objects, they are more biased, and the word bias is not an accident. They are more biased towards the higher density parts of the large-scale structure on the left. Blue galaxies, red galaxies, you get the point. So at the end of the day, we have this problem having to connect the visible to the dark universe. The dark is what contains, so the large-scale structure is what contains most of the cosmological information we are interested in, on dark energy, dark matter, gravity, inflation, as we'll talk about, as well as neutrino masses. But in order to access that information from our observations, this connection here is what we have to go through. This connection has a name, galaxy bias, and this is what I would like to talk in the rest of this talk. Okay, the rest of this is divided into 4 parts. So I'll continue next by making a little bit more precise what the definition of galaxy bias is. Then I will give you a very high-level description. I'm happy to discuss the details later. I'll give you a very high-level prescription of which methods we have available to make predictions for bias. Then I'll discuss the impact a good knowledge of bias has, or the critical impact that a good knowledge of galaxy bias has in cosmology by focusing in particular on tests of inflation and searches for primordial Gaussianity. And at the end, if I have the time, I'll say a few words on some physical effects that drive differences between the biases of dark matter halos and the bias of galaxies. Okay, so what's galaxy bias? So in a sentence, if I had to define galaxy bias, I would say it's the answer to this question. So if there's one thing you have to keep in mind for the rest, when I say galaxy bias, just the content of this slide. And so I'd say galaxy bias is the answer to this question. As I said, how does galaxy formation depend on its large-scale environments? So more precisely, the answer to this question comes in the form of a very famous equation known as the galaxy bias expansion. And what we have here is basically an attempt to relate the local number density of galaxies. So the left-hand side represents the number of galaxies that you would count in some volume at position X in the universe, and you want to relate that to the cosmic, the spatially averaged value over the whole universe of those galaxies. So there are 2 main pieces here. The one we've been focusing on is the one inside square brackets. And what we have here is an expansion over all types of large-scale perturbations, represented here by the letter O, that have an influence on the formation of galaxies. So here we're talking about density, tidal fields, gravitational potential in some cases. So there's a systematic way of making sure you are accounting for all of the operators. If you're interested in this kind of stuff, this review here is an excellent place to start. I'm just giving you, I guess, the essential description. So the name of the game here is to enumerate all of these perturbations. Once you're happy with the level of completeness of your list, this depends on the redshift and scales you are interested in. You simply sum them all up and multiply them by coefficients. These coefficients is what we call the bias parameters. And then I hope this makes apparent the physical meaning that these bias parameters have as the response of galaxy formation to changes in the amplitude of the several perturbations O that they multiply. So for example, we're going to see a few examples of this bias expansion, but one of these perturbations O is going to be the matter density contrast, so delta M. The corresponding bias parameter is called B1. So imagine you have a galaxy sample that has a B1 value of 2. What this means is that in regions of the universe that are 1% denser than the cosmic mean, you're going to find 2% more galaxies in that region compared to the cosmic mean. So it's in this sense that the bias parameters describe the environmental dependence of galaxy formation. So these bias parameters are only functions of redshift and of the properties of the galaxies you have in mind, like color, mass, luminosity, and so on. Importantly, and I will probably make this comment again later on, they are not functions of scale. So the phrase scale-dependent or the expression scale-dependent bias is one that appears often in the literature. There's no such thing as a scale-dependent bias parameter. As we'll see, what's scale-dependent is the relationship between different perturbations O that appear here. And yeah, basically here for the most part, I'm going to be talking about galaxy bias, but it's important or it's useful to keep in mind that you can always write down a bias expansion like this one for anything that you can think of measuring locally in the universe. So for the galaxy number density, we call this a galaxy bias expansion. For the halo number density, it will be the halo bias expansion. So if there's anything you can think of measuring locally in the universe, the number of galaxies, halos, voids, the power spectrum, the galaxy halo connection, and so on, you can always represent by an expression like this one. So one thing I haven't mentioned yet are these stochastic or shot noise terms. And this basically accounts for the fact that galaxy formation depends not only on large-scale fluctuations, but also on smaller-scale fluctuations. We call these stochastic terms or shot noise contributions. They're basically noise. They're important to mention. This is what I'm doing right now. They're also important to take into account when you make predictions for galaxy data. They're not the most interesting ones, I would say. Physically, this is important to take into account. But yeah, for the rest of this talk, I'm going to focus on the part that's inside square brackets, which is also known as the deterministic or non-stochastic part of the bias expansion. So what types of perturbations enter here? I already said the essential, which is what's repeated here in green. Basically, all types of large-scale perturbations that you suspect can have an influence on the formation of galaxies inside of them. So the usual suspect is the local density and tidal fields. So these are things involving second derivatives of the gravitational potential. As you go to smaller scales, you need to account for non-local terms, which involve higher than second derivatives of the potential. In cosmologies with primordial non-Gaussianity, we will see that the potential itself needs to be taken into account, but you can also have more exotic types of perturbations that are interesting to study if you want. But again, in short, if there's a perturbation that you suspect can have an influence on the formation of galaxies, then you must put it inside this formalism. Okay, this is an important slide. I'm spending some time here because it's important to understand this concept. So let me say exactly the same thing, but just with the help of this cartoon. What this equation is then telling us is that at cosmic mean, let's think of the galaxies as being uniformly distributed around cosmic mean. We can split our fluctuations into two types, short scale and large scale ones. The short scale are the stochastic terms. They add noise, if you want. They tell us whether a galaxy forms in one location and not its immediate neighbor. And then we have these most interesting long wavelength perturbations that coherently modulate the local number density of galaxies. And importantly, what's important here is that the strength of this modulation is what the size of these bias parameters controls. So for example, again, if you have a certain galaxy sample in mind that for perturbation O has a bias parameter that's 0, this means that those galaxies could not care less if the perturbation is there or not. So you can see that the fluctuation, so the local number density of the galaxies is not correlating with the amplitude of the perturbation here. If the bias parameter is positive, this means that you're going to find more of those galaxies in regions where the perturbation exists, but the bias parameters can also be negative, in which case you're going to find less galaxies in regions where the perturbation exists, or alternatively, more galaxies where the perturbation has a smaller value or a negative value. Okay, and what are the two main reasons then to study galaxy bias? So when we try to make predictions for galaxy data, you will see cosmological parameters that are going to be sitting alongside galaxy bias parameters, often with degenerate effects. And so that's reason number one. The greater our knowledge of galaxy bias, the greater our chances to break some of these degeneracies and obtain improved constraints on the cosmological parameters. Reason number two is simply turning the argument around. If you're more interested in astrophysics, you take your galaxy data, you put priors on cosmology from other types of data, for example, the CMB, and you fit for the bias parameters. And knowing what we know now, that the bias parameters describe a certain aspect of the galaxy environment connection on large scales, you're going to learn something about galaxy formation. Okay, most of the existing knowledge of biasing in the literature, so bias has been studied for several decades already, but a drawback that we can point out to all those works that they're for the most part highly focused on the bias of the dark matter halos, and that's ultimately not what we are interested in, because we still do not observe the halos, we observe the galaxies that live inside those halos. So the reason why galaxy bias studies have lagged behind halo bias studies is very simple. Galaxy formation simulations are a lot trickier than their simpler gravity only versions, which is what you need to study the formation of halos. That has changed recently in the last 5 to 10-ish years with the advent of projects like these ones here that have finally pushed galaxy formation simulations, which, let's call them, are sufficiently realistic, on to volumes that we can start calling cosmologically representative, so touching or crossing the 100 megaparsec mark. And I am going to be using, so some of the results that I'm going to show from here on out were obtained with either gravity-only simulations or with Illustrious TNG, which is one of these recent galaxy formation simulations. Okay, so how can we predict galaxy bias then? So let me outline three types of methods. As I said at the beginning, I'm going to be very high level here. I'm not going to go into too many details, but we can discuss them afterwards. So the first method is this one based on matter-galaxy endpoint correlations. Okay, so how does this work? So this is probably the simplest way to estimate a bias parameter. So here's on the top left, you have an example of a bias expansion. So delta G is now the galaxy density contrast, and to linear order, you can write it like this. You have a B1 times delta M. Delta M is the matter density contrast, and so B1 is the response of galaxy formation to changes in the overall density. So how can I measure this B1? So I can cross-correlate this thing with delta M to get the galaxy matter cross power spectrum, which is equal to B1 times the matter power spectrum. So what do I do now? I run a simulation. I measure these two spectra. I take the ratio of that on large scales. This goes to a constant, and you can simply, this constant is B1, which you can read out. So the reason why this deviates from a constant on small scales, high wave number, is because as you probe smaller and smaller scales, you need to account for higher order terms. In this bias expansion, you have to have delta M squared and tidal field squared. But just for B1, you focus on large scales and you can just read it out. So this is still probably how most people think about measuring bias, which is perfectly fine. Yeah. There will be a combination of both then. But taking the limit of infinite number of galaxies, which will be zero shot noise, this will still be the case. Actually, for this mass range, I don't think you're affected by shot noise here yet. Probably the upturn is probably what's causing that. It's a combination of two things for sure, yeah. But what I was going to say is that a slight drawback that we can point out to this way of going after bias parameters is that, as you can see, it relies on having sufficient statistics on large scales, which means a large simulation box, which is a more expensive box. And, I said that galaxy formation simulations are touching 100 megaparsec volumes, but that's still not 1 gigaparsec volumes, right? So there's still ways to try to estimate B1 from, for example, just probing this part, but it's not as reliable as having a good handle on what's happening on the larger scales. So if I would like then to estimate the other parameters that appear at second order, B2 and BK squared. BK squared is the coefficient associated with the tidal field. Kij is just the traceless part of the second derivative of the potential that it's meaning. So in order to go to second order in the bias expansion, to measure those parameters, I have to go beyond the power spectrum. I have to go onto the 3-point function or the bias spectrum. But the idea is still the same, right? You run a simulation, you measure the bias spectrum, you fit a model like this to it, and then you work out the values of B1, B2, and BK squared. The same volume requirements that were sort of penalizing the case of the power spectrum just become more exacerbated here because the bias spectrum requires more statistics. So the next two methods kind of overcome this difficulty associated with the volume. The next one is based on this new approach called galaxy field level forward models. So here's just a quick one-slide introduction to this technique. So the goal of this approach is to take some real-life galaxy sample. What you want to do is to reconstruct the initial conditions and cosmological parameters that gave rise to that galaxy sample, as well as the bias parameters that characterize that sample. So the way you do that, again, skipping over many details, you start off from the realization of the initial conditions. You forward evolve that using gravity to generate the forward evolved final mass distribution. So this is basically an n-body simulation or some approximation of it here. From here, you compute all of the operators that enter your bias expansion, the density, the tidal field, etc. You multiply them by bias parameters, you sum them all up, and you generate a realization of the forward evolved galaxy distribution, which you can then compare, and importantly, at the field level with the observed galaxy distribution. So like for anything, there are advantages and disadvantages with this approach. You can see my personal bias from the way I'm referring to them here. But yeah, the disadvantage that this is clearly highly numerically intensive. And this is not only because so per point in parameter space, I have to run an n-body simulation, this part over here. But the dimensions of the parameter space are crazy high because of the need to sample over the phases of the initial conditions, right? So so this is taking place on a grid. If I represent my density fields on a grid that has 100 nodes on the side, that immediately gives me 1 million parameters to sample for. So there are ways of dealing with that. So for the gravity part here, you can replace an n-body simulation with something faster, like second order Lagrangian perturbation theory. And to deal with the dimensions of the parameter space, there are sampling techniques based on Hamiltonian Monte Carlo methods that can help out, but still is very numerically intensive. The disadvantage is that you are doing the inference at the field level. And remember, this is a non-Gaussian field. So before I described methods based on the power spectrum and the bispectrum, so you're still not utilizing all of the information. Here, because you're doing the inference at the field level, at least despite the numerical intensity, at the end of the day, you're met with the comfort of knowing that you're utilizing in principle all of the information that is available in your data. So that's the.
Or you were talking about simulations. Here, you're talking about being not simulate. If you do simulations to get the bias parameters, you wouldn't have to do the million parameters, right?
Mm-hmm. Correct. Welcome to my next slide. No, sorry, no. This was just my outline of the key idea, right? And I motivated this disadvantage. And now, what's the way of overcoming that? This is the case for real latent applications, right? We're still a bit far away from super robust field level cosmological inference. However, as Joachim was just saying, if I'm just interested in the bias parameters of simulated galaxy samples, I can turn away from observed galaxies to simulated ones. And as pointed out, my life is now made way easier because now I don't need to sample the initial conditions nor the cosmological parameters because I chose them to run the simulation. So I can fit way more efficiently just for the set of the bias parameters. And this is what we've been doing. So this is just to give you an idea. We're going to see some of these results later on, maybe just towards the last part. So here I'm showing B2 versus B1 at the top and BK squared, the tidal bias versus B1. The only point that I want to make here is that the errors on these parameters, so every dot here shows the values of these parameters for a collection of galaxies in illustrious TNG at some redshift with some selection criterion. The point is that this precision here on these parameters would have been completely impossible to obtain on such a small box using the bispectrum method that I described before. So this goes to show the power of the field level approach and utilizing all of the information that's available at the field level. Okay, so finally we have separate universe simulations, my personal favorite for no particular reason. I just like the idea. So this is a technique that is based on something called the separate universe theorem. I know Allah doesn't like me calling this a theorem, but you can demonstrate this mathematically. So what can I say? And what you can demonstrate is that if you have local processes, so local structure formation taking place inside a large scale perturbation in some fiducial cosmology, you can show that that's equivalent to the same local structure formation taking place without any perturbation, but just in a modified cosmology. So in other words, let's look at this cartoon. Let's imagine galaxies forming in these boxes. What this is saying is that the galaxy that would form here cannot tell the difference between forming in this scenario or in a scenario where the perturbation is not there, but each box is just in a different cosmology. So if you want more precisely, what's happening here is that we're saying that the local physics in this box here regards or cannot see the structure of this large-scale perturbation. So they regard it just as a time-dependent change in the background. And the time-dependent change in the background is the change in cosmology, change in the universe, separate universe. That's where the name comes from. Okay, so then with this in mind, in order to make a prediction for a bias parameter using this technique, all you have to do is to run one simulation for one set of cosmological parameters that mimic a certain value of the perturbation you are interested in. You can ask me later which cosmological parameters need to be adjusted for different perturbations. That's interesting, but this is the key idea. Step number 2, you run another simulation for another value of for a set of cosmological parameters that mimics another value of the perturbation you are interested in, and then that's it. Now you just count the galaxies in these two simulations. You take duration, you normalize by the difference in cosmology, and from this you can very quickly read out the bias parameters. There are two key advantages here, which are especially relevant for galaxy formation simulations. The first one is that since with this trick, we can embed the whole box inside the large-scale perturbation. The box itself does not need to be large to resolve that large-scale simulation. Sorry, that large-scale perturbation. And again, this is especially relevant because then my simulation does not need to be 1 gigaparsec. So I can afford to have very high signal-to-noise measurements for bias parameters, even from a box like illustrious TNG, which only has 205 megaparsecs over H. The other significant advantage is that since your estimate is basically the ratio of the result of two simulations. You can and you should initialize those simulations with the same realization of the initial conditions. So different cosmology, but the phases of the initial conditions should still be the same. And as you take the ratio, you effectively cancel almost completely a cosmic variance. So you can really get high signal-to-noise estimates of bias coefficients, the bias parameters, with just a pair of simulations. So A and B is just my schematic way of describing just the difference in the cosmological parameters. So for example, let's imagine this is the bias parameter associated with density perturbations. So this will be B1. This will be the number of galaxies in the cosmology with a positive value of delta M. This would be the fiducial, let's say, and this would be the value of delta M. So the size of the perturbation.
B1 is not the only that with delta M.
Sorry?
B1 parameter is not the only parameter that respond to the change of delta M. B2.
Yes. So what you would do for B2, B3, and so on, you would run several separate universe simulations for different values of delta L, and then you just fit the polynomial to that, and then you can read out B1, B2, and B3 as the coefficients of that.
Because you change cosmology for A and B.
Yeah. Right, but okay, so let's say I have the fiducial cosmology, okay? And now I want to measure B1, I put the delta L. So the bias parameter that I measure from that will be the bias parameter associated with that fiducial cosmology, right? So the bias parameters though are not that strong functions of the cosmological parameters, but you're right. So do I have a better slide here for that? Possibly not, but basically let's think of one of these cosmologies B as being the fiducial one. Then this will be the bias parameter associated with cosmology B.
Omega matter is same thing, sigma E, what does it change?
Yeah, that's interesting. I think I have a slide. So here's an example of a few of these separate universe constructions. So for delta M, for total mass perturbations, the cosmological parameter that I have to modify is the total mass density. So omega matter, basically. And since this is just a matter perturbation, dark energy, radiation stays the same, this generates curvature. So these are also often called curvature simulations. Sigma 8, you mentioned that's important when you want to estimate a bias parameter associated with primordial non-Gaussianity, with the gravitational potential. So it's parameter I'm going to mention frequently in a second called B phi. So for that, you have to play with sigma 8, some isocurvature perturbations, some more exotic stuff. You play around with the cosmic density of the cold dark matter and baryons. And this is a really interesting one for tidal fields. The changing cosmology is not of any parameter itself. You just move away from an FRW spacetime to one of these Bianchi spacetimes. So basically, the box starts off cubic and then ends up like a slab. This is like super interesting. Like you can think of the scale factor goes from being a scalar to basically a vector. No, I rewrite Elasticity NG for Elasticity NG here. I'm in the code, and then I rerun it for different cosmologies. Okay, let me find my way where I was.
So you have to go to
Yeah. So there's something that we're doing here, which is another frequently asked question. We assume that the galaxy formation parameters stay fixed, right? When I change the cosmology, I keep the galaxy formation parameters the same. I say that the value of these parameters is what defines this galaxy formation model. Let me see how they respond to a change in omega matter or sigma 8. All right, so some more fun stuff, hopefully. The impact on cosmology, and I'm going to focus on a particular case of searches for local primordial non-Gaussianity. And so an accident why I'm choosing this, you're going to see, I'm going to motivate this. This is because here the degeneracy between cosmology and bias is perfect. And so, well, we'll get there. So here's a one-slide introduction to the parameter F and L, local type primordial non-Gaussianity. So phi here is the primordial gravitational potential generated during inflation. With all generality, we think it's close to Gaussian, or it is close to Gaussian for sure. You can always write it down like this. Some Gaussian random field plus some parameter called FNL times its squared, and when you have a squared Gaussian. So the square of a Gaussian field to itself, you generate something with skewness. That's non-Gaussian, and it's in this sense that FNL quantifies the leading order departure from perfect Gaussianity. So the technical FNL will be immensely profound. So knowing its value will teach us a great deal about inflation models, about what the physics behind the origin of the primordial density fluctuations, and more specifically, detecting non-zero FNL would let us rule out the simplest single field models of inflation, which would be, as written, quite profound, right? The early universe would not be as simple as it could have been. So here are here's a collection at the bottom of some constraints on FNL. They're all compatible with zero. The tightest one at the moment comes from CMB, from Planck, with a sigma FNL of 5. The latest from large structure tell us that give us a sigma FNL somewhere between 20 and 30. And this is a major target. Many people running forecasts for surveys like SphereX, Euclid, DESI, SK that tell us that in the future it will be possible to probe FNL with better than order unity precision. What I'm going to argue next is that at this stage, given our knowledge of biasing, we are in no position to trust these bounds here. We're still in no position to say that we can achieve a certain constraining power on FNL using galaxy data. Okay, so let me make that seemingly provocative statement clear. So when we say we're going after FNL in any competitive way using classical structure data, what we're really saying is that we're going to utilize this very famous effect called the scale-dependent bias effect, discovered back in 2007 in simulations by Dalal et al. So let me tell you where this effect comes from physically. It's important. So again, skipping over the derivation, you can show that in cosmologies with FNL, the galaxy density contrast contains to linear order at least two contributions, B1 delta M that we saw before, and B phi FNL phi. And what's important here are these two bias parameters. B1 we already saw, tells us how many more galaxies form inside large-scale mass perturbations. B phi tells us something similar, but slightly different. Tells us instead how many more galaxies form in regions of the universe where in the initial conditions there was a large-scale perturbation in the gravitational potential. The key point is that these are two galaxy formation parameters whose value is a priori unknown, okay? So now if I use the Poisson equation to relate phi to delta M, I arrive at something that looks like this, a scale-dependent coefficient that multiplies just delta M. This scale-dependent coefficient is what Dalal et al. And everyone since have been calling a scale-dependent bias parameter. But returning to a comment I made before, there's no such thing as a scale-dependent bias parameter. The fundamental equation is the one at the top. What you have here is two redshift dependent and scale independent bias parameters. What's scale dependent is again the relationship between delta M and phi, which from the Poisson equation, the second derivative, that's where this k squared comes from. So it's important to keep in mind that what we have here is not one parameter that becomes a function of scale. It's just another parameter B phi that enters the picture. So now if I take the power spectrum of this, the two living order terms are these ones, in gray, the square of the B1 squared. And this is how the galaxy power spectrum would look like for Gaussian initial conditions. If FNL is non-zero, then the product of the two gives you the living order term, which is this one here in brown, scaled as 1 over k squared. So it becomes important on large scales, but it generates this very famous scale-dependent signature whose amplitude is what you can use to constrain FNL. What's the problem? You kind of see where I'm going with this. The problem is that the amplitude of this signature is proportional not only to FNL, but also these two bias parameters, B1 and B phi, that we do not know a priori. So the fact that B1 appears here is actually not the end of the world, because B1 appears elsewhere. In particular, at the power spectrum level already, you see that B1 appears on small scales, where FNL doesn't contribute. So you can hope to use the smaller scale part of the data to put a bound on B1, which applies on cosmology, but you can also use the bias spectrum if you want to fit for B1. But even if you know B1 exactly, you're still left with the perfect degeneracy between B phi and FNL. So in order to constrain FNL using this signature, and I remind, it is this signature that stands a chance that gives us a chance at getting to sigma FNL of 1. But in order to use it, there's no way around it. We have to make some assumptions about this B phi parameter. So what people have done in the literature is the following. So they assume that there is a tight relation between B phi and B1. The most popular of them is this one called the universality relation. And the idea is very simple. So as I mentioned, B1 is a parameter you can measure from the data. In this relation, you fix the value of B phi. It's no longer a free parameter. This breaks the degeneracy with FNL, which you can then constrain. The problem is that if you go and check how these equations are, these expressions are derived, you will see that they are built on top of many simplifying assumptions. After reading this derivation, we will all be convinced that there are many reasons to expect them not to hold. And this is one of the things that I've been interested in quantifying how well or how poorly do these relations actually describe the real relations of galaxies. So this is one of the things I've been doing with separate universe simulations of the illustrious TNG. Again, to answer your question, I had to rerun the illustrious TNG galaxy formation model to other cosmologies. And what I'm going to put now on the screen is populate the B5B1 plane with different types of traces in the simulations and make a few points as I go along. So there are 3 quick points then. The first one, and this is starting off simple, so no illustrious TNG yet. So gravity-only simulations. And we find a really strong halo assembly bias signal. So let me tell you what this is showing. So in blue, you see the B5B1 relation for the whole halo population in different mass bins. So every dot here shows the values for halos at redshift 0.5 for some total mass bin. I'm not labeling the mass, but mass increases in this direction with B1. And then, so this is the blues for the whole halo population, and then in orange and green, you have the same thing, but just restricting to the 33% most concentrated and 33% least concentrated halos, and you see this strong departure with respect to the full halo relation. So this means that if we are to have a chance at predicting the B5B1 relation to galaxies, we need to understand not only how those galaxies populate halos as a function of mass, but also at least of concentration. Needless to say, the galaxy halo connection as a function of mass and concentration is something that we still do not know very well. Moving on, so now putting some results from the illustrious TNG. Now in red, you can see the relation for galaxies in stellar mass bins. In purple, in bins of the black hole luminosity, so the black hole mass accretion rate. All of the neutral hydrogen at redshift 0.5 is the relation here by the cyan point. Again, you can see that the B5B1 relation is a very sensitive function of depending on how we choose to select the traces in the simulation. There's a very rich structure here, which importantly is not well described by this very simple universality relation. So that's really the key takeaway point from this slide. This is, I think, the main slide of this part of the talk. Everything that I'm going to say follows from this takeaway point, which is there's currently a large theory uncertainty on the B5B1 relation. So there's this spread here is something that we've been ignoring in all our FNL constraints and forecasts. So these are just the first ever predictions that I'm at least aware of. So they were obtained with just a single galaxy formation model, which is illustrious TNG. So we still do not know, for example, how these relations change or how they depends on what I choose to assume about galaxy formation. If I use one of the other galaxy formation models that are out there. And even if we understand this relation really well from simulations, to establish the connection between that and observation is something that's always very tricky. Okay, so there's currently a large theory uncertainty, and another thing that I've been interested in is in understanding how does this uncertainty then affect the resulting constraints on FNL. So this is what I did in this paper, where more specifically I took the power spectrum of both the R12 galaxies, so real data now, and I happily went away constraining FNL by making different yet plausible, all plausible assumptions about the B5 parameter. So this is what you're seeing here. This is the main result. The upper panel shows FNL, the FNL constraints. The lower panel just shows the error bar. This is shown as a function of this P parameter, which has nothing fundamental to it. It's just a convenient way to parameterize the amplitude of B5 at fixed B1. I'm also listing the values of B5 here. Importantly, they go from 10 to -3. This was chosen to stay inside the range that we're finding in simulations. Okay, so 2 quick points here. The first one is that I hope it's clear. The constraints are completely dominated by what I, as the user, chose to assume about the B5B1 relation. So I have here 7 constraints on FNL. They're all very different. So the error bar can vary by over an order of magnitude. Which one is the correct of these 7? Well, I do not know, because I do not know which value of B5 is closer to the actual value of B5 of the boss galaxies. I know that order unity uncertainty on B5 matters because FNL is also expected to be of order unity. So if it multiplies the parameter whose uncertainty is order unity, then I'm not really constraining FNL. You can see, for example, there are several cases here. So basically all of them can kind of count them as being order unity, and yet the constraints can vary very significantly and One of the reasons is because B5 can be a small number, actually. So it's not too hard for you to find samples where B5 is close to 0, which means if you are analyzing those galaxies, FNL could be 1,000, and you would not see the scale-dependent bias signature because the B5 value is very small. So this is the bad news. The good news is that if we pay attention to the actual numbers, you see that the significance of detection is not affected. So the tightest constraint here is 16 plus or minus 16, so 1 sigma detection. Detection, I mean, quote unquote, right? Just 1 sigma significance. This is the tightest one. The loosest is 200 and something, plus or minus the same 200 and something. This is often used as an excuse, I see, to making it fine to assume some random value for B5 to constrain FNL. This is obviously, I think, not the case. And the quickest way to argue is against that is by simply asking you to compare these two constraints, FNL of 0.1 plus or minus 0.02 versus 20 plus or minus 4. These are two bounds that we could obtain with the same data with different values of B5. They're both 5 sigma, but of course we'll be interpreting them very differently, right? We would celebrate this error bar a lot better than we will celebrate this error bar. This is compatible with Planck, this one is not. So it does matter for the interpretation what you assume for B5. So if you're just interested on the significance of detection, then the honest or the correct thing to do is to fit for the parameter combination FNL times B5, which is what the data is truly telling you about.
If B1 is 1,
Mhm.
for example, for the matter density distribution, then we believe that B5 is 0. Do you also get P1 in this case or something else?
If B1 is equal to 1,
But it's not like B1, but it says if you consider matter distribution as galaxies,
Huh.
and do you see any different value? For example, in your equation, if P is not 1, exactly canceling, if that is not exactly canceling the B1, you will see some effect.
so you're asking, so basically,
Is there?
what's the B5 value of matter?
Yeah. Exactly.
The B5 value of matter should answer. Shouldn't. That should be 0, right? Otherwise, you would see it in the simulation. You see the same turnaround.
Very alive.
For tracers, for galaxies, right? But for matter, B5 is 0.
Be something subtle such that it forces P goes to 1 or exactly B1 when you approaches the matter distribution.
Is that true? I'm able to think because if I'm just describing matter, the galaxy bias expansion for matter, or the bias expansion for matter is just delta M equals to itself. There's nothing else, right? So I wouldn't.
Is fixed. So it's enforced in the formula that the effect vanishes for the matter distribution.
Yes.
In here,
I'm not sure if I can from there, because that assumes you're looking at traces, that you're looking at peaks of the density distribution. When you derive the universality relation, the starting point is, let me look at peaks of the density distribution. So if I'm looking at peaks, I'm no longer looking at the whole matter field, right? So I'm already, so I wouldn't go, I don't think we can read too much into the fact that when P is equal to 1 for matter, this is naturally 0. I think it's just 0 because it makes no sense to even invoke B5 for the matter. No, that for sure we don't. No, that's for sure. I want to leave clear. Like for matter, the power spectrum does not have this upturn on large scale. This is only something that is for biased tracers. So something that at least has a non-zero value of B5, and delta M has B5 equals to 0. Like this trivial case where the bias expansion is just delta M equals to delta M.
Some of these cases, like 0 is not in the 1 sigma thing.
Sorry?
So like in orange or purple or pink, 0 is not part of the 1 sigma thing. Like if you 230 plus minus 226, so you will never get 0.
But it's compatible with 0 at 1 sigma, right?
So the number says 230 minus 226, which is larger than 1. That's what it said.
And what's the problem with that?
It's more than 1.
Okay, fine. Okay, okay, fine. Approximately. I mean, there's also sampling issues here. I mean, it's not pretty too much. It's
The Planck being the most constrained, 0 was always part of 1 sigma.
Yeah.
And here it's not a problem. Like it is possible.
Yes, yeah. Don't read too much to this 1 sigma. I mean, we shouldn't. 1 sigma, you don't start calling a detection, right? This depends also on the range of scales that you utilize and so on. This is just let's not read too much into that. But my key point is that you shouldn't trust any of these 7, right? That's my point, right? I mean, this is, by the way, 16 plus or minus 16 is the tightest ever constraint obtained using large structured data, reported in abstracts. Do I win a round of applause? No, that's the point. Right? Any of you could have continued these plots to the left, increasing the precision. That's the key point, right? You control how tight you want the error bar to be, basically. Okay, so I'm just making this point here on the significance of the detection, and this is something that I really want to emphasize. I think we need to start paying more attention to this important, even if subtle, distinction between what it means to constrain and to detect FNL. To constrain FNL, I say it's to say it's equal to something plus or minus something. This is what the CMB does, and automatically, if you constrain, you have a chance at detecting. In large construction, unfortunately, outside of bias assumptions, we can only constrain this parameter combination, so we can only afford to detect FNL. But in order to go from a detection or for a bound on this to a bound on FNL, we have to go through these unknown bias parameters. So this is not a two-way street. So I asked in that paper, can we actually constrain FNL? So in short, to wrap up, the answer is yes, but only if we understand galaxy bias a lot better than we currently do. And this is the perfect example of the close interplay between bias and cosmology, because here the degeneracy is perfect, right? So to finish this part, this is my personal opinion. What is it that I think we should be doing now? So first, we should acknowledge that we understand this relation way less than we have been assuming, and as a result, we should start at least also quoting bounds on the parameter combination FNL times B5, which is what the data is truly telling you about. And note, there's value to doing this, because if you detect this parameter combination, even though you would not know exactly what FNL is, you can still distinguish it from 0, which will still teach you something about inflation. Okay, then we acknowledge we have a poor understanding of this P5B1 relation. So this motivates, I think, the development of simulation-based research programs aimed at improving this understanding. This is, of course, challenging. Also, what makes it fun. We're talking about understanding galaxy information to a level that I think we're still a bit far away from understanding. But, apologies for the cliche, with every challenge comes an opportunity, and the opportunity here is, should we succeed even roughly in understanding in which direction in B5, B1 plane certain galaxies tend to be? This gives us a tool to optimize our galaxy selection strategies, to try to identify the galaxies that have the largest values of B5. Those are the galaxies that should give you the tightest or the strongest chances of at least detecting FNL. And along the same lines, I think when we assess the relative performance of different surveys and as we plan future surveys, I don't think we are in a position where we can continue to ignore discussions about the PNG bias parameters. You have a question?
So since you haven't really shown different height simulations, there still remains the possibility that they actually predict exactly the same thing.
Yes. It's possible, yeah.
And since this is trying to understand whether this is really large scale as well. So it's essentially
the signatures on large scales, on the power spectrum appears on large scales, but the physics is very small scales. It's galaxy formation physics.
Is it?
There is
what would change the signal what would you have to change in the recipe of galaxy formation to make this scaling relation that you have, that was not universal, but it's a scaling relation, right? Break. I mean,
is it not broken already by this?
I don't know. I mean, you take your galaxy, you take your crystal you want, you get prediction. It's not universal, it's a prediction.
Yes, well, yes, exactly. Perfect. Yeah.
Obviously, prediction doesn't change as galaxy formation.
Correct. Okay-ish. Then you fix point number 1 here. Let's say that happens. Like I run Illustration MG, Eagle, Horizon EGN, etc. And for stellar mass selected galaxies, they all give me the same relation. They're all on top of the same Rev 1 here for Illustration MG. So this would be amazing news. This means this relation is at least robust to several galaxy formation scenarios. So the next step would be, okay, let's apply the same selection strategies or cuts that are made in real surveys onto the Illustration TNG. But yeah, there will be like if that's the point that I wanted to make here. If we need to determine how sensitive this is to different galaxy formation. I mean, it's very similar to what you're doing with the baryonic effects on small scales. But here we're just looking at a different prediction from these hydrodynamical simulations. Will they agree or not?
Could you come up with reasoning, analytical reasoning why we keep changing, for example, the change back? It's not completely obvious to me what would happen.
So basically here for B5, you're asking is basically how is the change in sigma 8? So how well will these simulations compare? If you change sigma 8, run the simulation again, compare them, and do they agree or not? Basically, that's the question. And this is something, of course, we're working on at the moment. Yeah, I think I just have the essential here. Like plots like this are very common comparing the performance of different surveys. They're also very misleading. For example, just to highlight, this is saying at face value, if you read this, that mega mapper is going to perform better than SphereX. How can I possibly make that statement if I do not make any statement about what I expect the B5 values of mega mapper to be and the B5 values of SphereX to be? So going forward, there's at least one thing we need to ensure from our simulations is at least that we're not looking at galaxies that have really low values of B5, because those would be bad galaxies to go after this signature because they're not very responsive to it.
What are they assuming?
Always universality relation. Yeah, always this dashed line here. All right, so I'm gonna have to ask you now, do I still have 5 minutes for this part? This is going to be this is a short one. I'm happy to end here as well. I'm in your hands. Okay, this is going to be really quick. So I just want to make here 3 quick insights on what drives Halo galaxy bias. We can discuss the minutiae afterwards or in the afternoon. So so what drives the difference between the bias of halos and the bias of galaxies? So this is my last slide then, really quickly. What I'm going to do is to progressively build up an equation that's going to relate the bias of galaxies to the bias of halos. And I'm going to make only one assumption, which is that the galaxies live inside the halos, which when it comes to assumption in astrophysics, it doesn't get better than that. So here's step number 1. This is an equation that is super popular in the literature, followed by a sentence that says that the bias of the galaxies is a weighted version of the bias of the halo. So you are integrating over all of the halo masses, the halo mass function, and the HOD, the halo occupation distribution, which is the mean number of galaxies in halos. And this simple effect alone, let's call it HOD weighting, immediately drives some differences between the bias relations of galaxies and halos. So here's an example. The B2B1 relation, the dashed line is the relation for, the dashed black line, sorry, is the relation for halos. And every gray dot here shows the outcome of this expression applied for B1 and B2 for the random selection of HODs. And you can see that this always pushes the values of B2 upwards. This is very easy to demonstrate. The relation of the halos has a positive second derivative for any HOD. This always shifts the point upwards. This equation at the moment is general, right? So whichever bias parameter I'm interested in for the galaxies, I should use the same bias parameter here for the halos. So for example, for B1, I should use B1 of the halos here. For B2, I should use B2 of the halos. Yeah, but I can always write it down as being BG equals to, well, under certain assumptions that I'm going to make in a second, I will just plug B2 over here. B2 of the halos. It's not correct because I'm still ignoring, I'm still putting stuff on this equation. There's a certain point that I'm going to mention in a second. And you can kind of see evidence of this effect already in our illustrative results. You can see that points are being shifted upwards. Okay. This P2B1 relation can actually be measured from real data using the power spectrum on small scales or the bias spectrum. Here's a collection of some of these estimates. We're still not in a position to say we have detected this difference of galaxy and halo bias relations, but hopefully in the future with DESI and Euclid and so on, we might be able to distinguish this and maybe hopefully start to say some things about galaxy formation. The second point I want to make here is just a continuation to this. Of course, we expect the bias of the halos to be not only a function of mass, but of other halo properties, particular concentration. Let's call this halo assembly bias, but we're still dealing with this, still dealing with the same effect, just made more complicated by the fact that now we have two halo variables. So the point that I want to make here, and this is something I already before when I talked about the strong halo assembly bias signal and the B5B1 relation. This means that if there's a complicated dependence here on mass and concentration, depending on how galaxies populate halos as a function of mass and concentration, the galaxies are going to inherit some of that signal as well. And the figures are here just showing a collection of the impact of concentration on a bunch of bias relations. We're still in the process of understanding exactly what's going on here. I think there's something interesting to be learned about structure formation, because we see an impact of assembly bias on some bias relations, but not on others. So the B2, B1 seems remarkably unaffected, regardless if we're looking at low or high concentration halos. High concentration halos tend to have a tidal bias that is pushed downwards, but tend to have a B5 value that's pushed upwards. And I'm still not sure what, but I think there's something interesting to be learned about galaxy formation from this, from results like this.
So this will skew your sample towards if you higher concentration towards higher mass halos.
No, this sorry, I'm being too quick here. This is at fixed mass. So I'm dealing with mass, and then I split in concentration. And finally, this is a term that we were missing, and now this equation is only valid for the linear bias parameters. And what was missing here is this thing I'm calling HOD bias. It's very easy to see that this has to be here, analytically, straightforward, but even just with words, this equation is telling us that the bias of the galaxies is a weighted version, so it's an integral over the halo number density, the HOD, the halo bias. What's the halo bias? It's the environmental dependence of the halo number density. So we're missing the environmental dependence of the HOD. We're missing how the galaxy halo connection varies from position to position as a function of large scale perturbations. And this is what this thing is describing. And this is now, if this would be B2, now what you will have is basically the second derivative of this thing, of the HOD response as well. So the equation will get more complicated. So with the help of a cartoon then, to finalize this, what this is saying is that the bias of galaxies is then a combination of two biases, the bias of halos and the bias of the HOD. The bias of the halos, again, tells us how many more halos form inside the large scale perturbations, and this HOD bias is telling us how many more galaxies form inside the halos that live inside the perturbations. So to any of you that are working on building, for example, HOD galaxy catalogs, an assumption that is often made is that you assume that this HOD function, the galaxy halo connection, is the same everywhere inside the box, but this does not necessarily need to be the case. You can have environmental dependencies. Does this matter? Well, depends on the perturbation you have in mind. We're finding that for the case of B5, we're finding that these HOD bias terms can actually be quite important. So what we have here, B5 is a function of redshift for galaxies with this stellar mass. These dots show separate universe results. The solid line shows the outcome of this equation where I set this to 0 with all the other ingredients measured from simulations. These HOD biases is also something you can measure using separate universes. And once you plug that into the full equation, you get the dotted lines, which represent the actual measurements much better. So these HOD bias terms can be important for certain types of perturbations and bias parameters. Okay, so this is my summary slide. I was progressively building it as I went along. I know that I'm already past time, so I will end here, and thank you all for listening.
To understand it's HOD bias. So if you would take sham instead of HOD, would that be included? So that some other way of populating galaxies with including merger-free information if you want.
Yes, in that case, yes. I think so.
So if we look at the HOD, can you use this analysis? Can you say something about
In that case, the only assumption you're making is just that after you rank order them, there's a one-to-one connection, right? Which is an assumption. Fine, we can discuss its validity or not, but it's sounds reasonable. In that sense, then you just have to inspect basically. Then after you do that, you can still measure an HOD, right? And see if it's varying from as a function of position, or if it's correlated with the local density. So you can inspect, maybe that way you can have a chance at inspecting the size of these HOD biases. The point that I wanted to make here is that in proper HOD approaches, where you specify the function, like you specify the halo, the Gaussian halo connection, right? So this will be some function of mass and concentration. If you just do that, you're missing out on this additional effect. In abundance matching, you have at least to give the chance for this environmental dependence of the HOD to be there. But you're not enforcing it to be zero or to have a certain value, which is what you do in proper HOD catalog building.
Just to clarify, do you use this forward modeling to get the bias parameter, or do you use power spectrum and bias spectrum to get the bias parameter?
For this talk, I think I've only used the power spectrum to get B1 in this plot. B5 came from separate universe, but B1 could also come from separate universe. Actually, now I'm not 100% sure. Maybe these B1s actually also come from separate universe, but they give you the same result. For all the results on B2 and BK squared, like for example, this one here, and let me get him. So these are all forward modeling. I could not possibly, with such a small box, I could not have possibly gotten to this precise bias estimates if I would be using the bispectrum on just this small box. This again, this goes to show the power of the forward modeling approach. So this is no, not yet, not yet. So this is still just a cubic box. So here we have forward modeling, separate universe.
So for the B5 story, this is all about using this scale-dependent in the power spectrum. Shouldn't there be an independent constraint in what is Yes.
That's the point. It is not competitive, right? So I try to emphasize as I went along that in order to reach the sigma, there's a reason why local FNL is more popular than equilateral and what's the other one? Folded or orthogonal, because it has this effect in the power spectrum, so it gives you a chance to get to this sigma order unity. Without that, then you get just like order, I don't know, 50 or 100, like, or they don't quote me on this, but it's not as competitive. But things can get worse, right? So in the bispectrum, you're right. The bispectrum depends on FNL through terms which come from the primordial bispectrum. So the FNL does not come attached with a B5 value. So schematically, then FNL enters in three main terms, which are these three. So at the bispectrum level, we have to worry about another bias parameter, B5 delta. So if you do not assume anything for B5, then what you should do is to treat this whole thing as a free parameter, FNL as a free parameter, and this whole thing as a free parameter. What I've been finding is that, so this is again another unknown parameter, and what I found was that if you treat this as a free parameter, turns out that this is very degenerate with this. So even the bispectrum alone that could probe FNL without B5, as you marginalize over this term, you wash away the primordial signal as well, which is annoying. So in other words, this is to say the bispectrum can only improve on constraints on FNL if you assume something for now two bias parameters, B5 and B5 delta.
Question? Any question online? If not, let's jump Alex again.
Thank you.